Hi everyone, this is lesson Gravitational Fields. In this lesson, we are going to learn how gravity works between objects, how Newton's Universal Law of Gravitation is used, and how we can connect the Universal Gravitational Constant with Gravitational Field Strength. By the end of this lesson, you should be able to explain what affects gravitational force, use the gravitational formula, calculate the value of g on another planet, and solve a net gravitational force problem using vectors. So let's start with Universal Law of Gravitation. So, gravity is a force of attraction between any two objects that have mass. So, any two objects having mass will exert force on each other, and this force is called as gravitational force. That means Earth pulls on you and you pull on the Earth. The sun pulls on the planets, and even the two small objects in a room technically pull on each other. So, any two objects having some mass will pull on each other with the force of gravitational force, and this force is weakest force. The reason we usually do not notice the force between any two small objects is that their masses are too small, so the gravitational force is extremely tiny. Now, let's write the law in words. So, gravitational force between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So, this force is directly depends directly on product of the masses. So let's say object 1 has mass m1, object 2 has mass m2, so it would be the product of their masses, and force depends inversely on the distance between the centers. So as you can see, we have to mark the distance between the centers. So this is the center of object 1, this is the center of object 2, and this line joining the centers would be the distance under consideration. So this force depends inversely on square of this distance. So this distance is r, so it will depend inversely on r square. So the law becomes Fg is directly proportional to m1 m2, and then Fg is inversely proportional to r square. Now on combining these two equations, we will get Fg is proportional to m1 m2 by r square. Now in order to remove the proportionality sign, we always write a constant, and in this the constant is universal gravitational constant g m1 m2 by r square. So where g is universal gravitational constant, the value is 6.67 times 10 raised to the power negative 11 Newton meter square by kg square. So universal means this value of this constant will never change, no matter what the medium is, so its value remains the same. Again, the common reminder is we have to use center to center distance for this force. Now let's move on to the other part of the lesson, which is one of the property of gravitational force, that gravitational force is always attractive. So gravity never pushes objects apart. It always pulls objects towards each other along the line joining their centers. So if we have object 1 and object 2, object 1 pulls object 2 towards itself, and object 2 pulls object 1 towards itself. So let's draw. So this is mass m1, this is mass m2. Now object 1 will pull the object 2 towards itself. So this is how it exerts force on m2. So m2 would have the tendency to get attract towards m1. So this is the force on object 2 due to 1. And similarly, object 2 is going to exert a pulling force on m1. So this m1 has the tendency to get attract towards m2, and this is the force on 1 due to 2. Right. So as you can see, m1 would have the tendency to go on to the right side, and m2 would have the tendency to go on to the left side. This is how these forces will be drawn. Now we have to explain why the forces are equal and opposite. So F21 or F12 equals F21. So both the forces in their magnitudes, they are equal. So if object 1 is exerting 2 Newton force on object 2, so object 2 will also exert 2 Newton force on object 1. So these forces are equal and opposite, which leads to the connection between Newton's third law, which states for every action there is equal and opposite reaction. Right. So what happens in this case? This force, as you can see, in terms of magnitude, they are going to be same, and in terms of direction, as you can see, they are opposite. So now in the vector form, we can write F12 equals negative F21. It means the magnitude is same. That's why we have mentioned the equality sign. And negative implies that the direction of F12 and F21 are opposite to each other. As you can see, F12 is in the right side direction and F21 is acting towards the left. So these forces are equal and opposite in nature, connecting to Newton's third law of motion. So Newton's third law of motion. Now let's explain why the motion can still look different. So let's say we have an object Earth, and then we have any other object like Apple. So we have seen the evident motion is Apple is attracted towards the Earth, and that's why it falls towards the Earth like this, and this is the direction. So we can write force on Apple due to Earth, and the motion is in this direction, and this is how the force applies. But as we have seen that universal gravitational law can be connected to Newton's third law of motion, so if Apple is being attracted towards the earth, so earth should also be attracted towards the apple, and earth should have the tendency to move towards the apple. So the force will be in this direction, and this force will be force on earth due to apple, due to which apple is exerting the force on earth, which has the tendency to pull the earth towards itself. So as you can see, both the forces are in opposite direction, but and both the forces are equal as well. But this motion is quite not evident, but this motion is quite evident. Now the question is why? Why this motion still look different? So motion depends on the masses also, because motion means acceleration. So if we have more mass, then we have less acceleration. And as you know that the mass of Earth is large. So its acceleration of Earth would be less. So mass of apple is small, so acceleration of apple would be more. So that's why we see apple falling towards the earth, not the other way around. And we have already seen the connection of universal gravitational law to Newton's third law of motion. So again, this is clear. If earth pulls on an apple, does the apple also pull on the earth? Yes. With which force? With equal force. But why do we notice only apple moving? Because of the masses. Since mass of earth is bigger, that's why acceleration of earth is less. And mass of apple is less, so that's why acceleration of apple is more. So this is how it is connected. Now we are going to connect capital G and lowercase g. This is an important distinction. Capital G is universal gravitational constant. It has same value everywhere. That's why it has name universal gravitational constant. So this G has value 6.67 times 10 raised to the power negative 11 Newton meter square per kg square everywhere. So this value is constant everywhere, right? And this small g, which is also acceleration due to gravity and gravitational field strength, this value varies, or gravitational field strength. So this value varies. So we have to find the relation between this capital G and lowercase g. So on Earth near the surface, we often use g as small g as or lowercase g as 9.8 meters per second square. But this value is not constant everywhere, it changes. So now we have to find the relation between this uppercase g and lowercase g. So first we will assume that there's any object on any planet. So let's say we have object with small m mass, which is present on the Earth, let's say on the planet Earth, and whose mass is me. So this is Earth, and the mass of this planet Earth is me. And this is m, which is the mass of the small object. So this Earth is exerting the force on this small object with whose mass is m, and this would have tendency to go towards the center of the Earth. So we have to write what are the forces that are acting on m. So as we know, gravitational force acts on m, and that force can also be written as per Newton's second law of motion, m times acceleration. So since it's acceleration due to gravity, so I will write Fg equals mg. And due to universal gravitational law, we will write Fg equals capital G m1, which is this mass of object which is small m. Then we have other mass as Earth, whose mass is me over r square. So let's say the distance of this object m and the Earth is small r. So I would write r square. Now we are going to set the equations equal, which is because Fg equals mg, Fg equals this, so we can equate the right hand side of the both equations. So we can write mg equals gm me by r square. Now we can cancel the small object's mass, so it would be cancelled like this. So g equals capital G AB over r square. So this is the final relation that we will get. So small g, or acceleration due to gravity, equals universal gravitational constant times mass of Earth over r square. Now we have taken mass of Earth here. We can take any planet, so it would become mass of that planet, and r is the distance between the object and the center of that particular planet. So this is the relation. Now let's solve Eris problem. So Eris is a dwarf planet with an estimated radius of approximately 1200 kilometer. A rock is dropped from the rest near the surface of the Eris from height of 0.30 meter. It takes 0.87 seconds to reach the surface. Calculate the value of g on Eris. Calculate the mass of Eris. If a rock is dropped from the rest from the height of 2.50 meter on Eris, calculate how long it takes to reach the surface. So now let's write the given information. So first of all, we are given with the radius of the Eris, which is 1200 kilometer. So we can write radius is 1200 kilometer. And then we are given with a rock is dropped from the rest near the surface of the Eris. So from rest means initial velocity is 0. So we can write Vi is 0. And it is released from the height of 0.30 meter. And it, so we can write first displacement. Delta D equals 0.30 meter from which it is being thrown, and then delta T is also given to us, which is 0.87 seconds. Now we have to calculate the value of G on the Eris, which is unknown for part A. So small g we have to calculate. For part B, we have to calculate the mass of Eris. So we can write mass of Eris, E represents Eris, and in part C, we have to calculate if the rock is dropped from rest from height of 2.5 meter, calculate how long it takes to reach the surface. So here the height has been changed, then we have to find the delta T. So first unit conversion is needed. As you can see, R equals 1200 kilometers. So we have to write this in SI unit. So I will multiply this with 1000 so that it becomes, so the distance becomes in meter. Now we have converted the distance into meters, and we can write this also in scientific notation, which will be 1.2 times. As you can see, if I will write the decimal here, I will count the digits after decimal: 1, 2, 3, 4, 5, 6. So it would be times 10 raised to the power 6 meters. So this is the scientific notation. And let's start solving this. So first, in part A, we have to find the small g from the falling rock. And you can see that we have already determined the relation between g and capital G. So let's see if we can use that. So g is capital G, mass of the planet. In this case, it is Eris, over the distance we are taking as r square, which is already given to us. Now you can see that we know the value of g, but we do not know the mass of Eris, so we cannot use this formula. So we have to switch to kinematic equations in order to calculate the g. So I can write delta d equals, I can use the second equation of motion where delta d equals vit plus half a delta t square. And it's vi delta t. Now I will substitute the values in this equation. As we know, delta d is 0.30 meter given to us. Vi is 0, so this whole product becomes 0. Plus half a can be replaced by g, and delta t is 0.87 square. Now I can just rearrange the equation, which is 0.30 equals half g 0.87 square. Now I can calculate this. 0.30 times 2 over 0.87 square will give us g. And on solving this, we will get approximately 0.79 meters per second square. So I can write it is 0.79 meters per second square as g. And as you can see, it is much less than the acceleration due to gravity on Earth, which is 9.8 meters per second. Now we have to convert the radius of the Eris, which we have already done earlier. Now for part B, we will find the mass of the Eris. So for this, we can use the relation G equals G mass of Eris over R square. Now I can just substitute the values. Since we got G in part A, I can substitute it. 0.79 equals, I'm substituting in this formula. Capital G we already know, 6.67 times 10 raised to the power negative 11. MB we need to find. R we have already converted into meters. 1.2 times 10 raised to the power 6 square. Now again on rearranging, we will get the mass of Eris, which is MB. So on rearranging, we will get 0.79 times 1.2 times 10 raised to the power 6 square divided by 6.67 times 10 raised to the power negative 11 equals ME. This will give us the mass of Eris. And you can again solve this using the calculator, and you will get the mass of Eris as 1.7 times 10 raised to the power 22 kg. So we will get 1.7 times 10 raised to the power 22 kgs would be the mass of Eris. Right? So we have just used the relation between capital G and lowercase g in order to determine the mass. And then we have rearranged the equation. Now for part C, we have to find the time for a 2.50 meter drop. So for this again, we can use the second equation of the motion, kinematics equation. So which is delta D equals Vi delta t plus half a delta t square. So since initial velocity is 0 because the object was dropped at from rest, so Vi delta t will become 0. So I can just remove this factor. So it would be delta d equals half a delta t square. Right. So it would be delta d equals half a delta t square, and a, that means acceleration due to that planet we have already calculated, which is 0.79. We can just plug in the value, so we can just substitute the values here. Delta d is 2.50 equals half, g is 0.79, and delta t square. Now on rearranging, we can rearrange this, and I will get 2.5 times 2 divided by 0.79 equals delta t square, and I'll use the inverse operation to find delta t. So it will give us 2.5 seconds. So delta t would be 2.5 seconds. So we have calculated part C. This was part B, which we got mass of Eris, and this was part A, which gave us acceleration due to that planet gravity. So this we have seen that how we have to use the kinematics equation in order to determine acceleration due to that particular planet, and then we have used the relation between lowercase g and uppercase g to determine the mass, and again we have used the kinematic equation to determine the time that the rock will take on changing the. Now we are going to do one more example involving gravitational forces and vector addition. This question only uses the perpendicular arrangement. So uniform spheres A, B, and C have the following masses and center to center distances. Masses are given to us and center to center distances are also given to us. The only forces acting on sphere B are the gravitational force due to A and C. For the perpendicular arrangement shown, determine the net gravitational force on B, include both magnitude and direction. So as you can see in this diagram, object B is going to experience force due to object A and due to object C. Now, object A is going to pull object B towards itself, and you can see the direction of force, gravitational force on B due to A. So this is FBA. And then you can see object C is also going to pull object B towards itself. That's why it's going to experience the force towards C, which is FBC, which is force on B due to C. So these are the two forces, and since you can see these two vectors are arranged perpendicularly, so FBA and FBC. Now, since you know that forces are vectors and vectors can be added using vector addition, so here we can use the triangle law to determine the net force. So after calculating FBA and FBC. Now, how we can calculate FBA and FBC? We can use Universal Law of Gravitation, which is capital G m1 m2 by r square. Write the given information. So we are given with mass of A, mass of B, and mass of C. Along with that, we are also given with RAB and RAB and RBC. So mass of A is 40.0 kgs, mass of B is 60 kgs, mass of C is 80 kgs, 60.0 kgs, 80.0 kgs, and we are also given with RAB. RAB is 0.50 meters, and RBC is 0.75 meter. Now, so we also know the forces direction, which is FBA, which is acting towards west, and FBC, which is acting towards south. Now, step 2 is to calculate the first force, which is FBA. So, we will use capital G MB MA over RBA square. We have used universal gravitational law for this. So, now I will plug in the values. So, it would be 6.67 times 10 raised to the power negative 11 times mass of B, which is 60.0, mass of A, which is 40.0, over RBA square. RAB or RBA is 0.50 meters, and I will write the square. Now you can solve this, and on solving FBA, we are going to get 6.4 times 10 raised to the power negative 7 newtons, and you can see the direction is towards left. I can write west. Now we will calculate FBC. So if for FBC also we are going to use the same gravitational formula. So it would be capital G MB MC over RBC square. Now we are going to plug in the values. So we will get 6.67 times 10 raised to the power negative 11. MB is 60.0, MC is 80.0 kgs, and RBC is 0.75 square. Now on solving this, we are going to get FBC as 5.7 times 10 raised to the power negative 7. 5.7 times 10 raised to the power negative 7 newtons, and the direction is south. So I will mention south because force is a vector. We have to mention the directions. Now we have to find the magnitude of F net, for which we can use the triangle law. So as you can see, one force is towards west, one force is towards south, and I will complete this triangle, and this would be the direction of the resultant force, which is F net. Now, in order to find the direction magnitude of F net, we are going to use the Pythagoras theorem because we are given with FBA and FBC. So write F net equals square root of FBA square plus FBC square. We will plug in the values. So FBA is 6.4 times 10 raised to the power negative 7 square, plus FBC is 5.7 times 10 raised to the power negative 7 square. Now on solving this, we will get 8.6 times 10 raised to the power negative 7 newtons. So this is the magnitude of F net. Now in order to find the direction, or we can determine the angle for the direction. So we are going to use trigonometry, tangent ratio. So tan theta equals, as you can see, this is the angle that we need to find, which the resultant is making. So we can write tan inverse or tan theta equals the vertical component over the horizontal component. Vertical component is FBC over FBA. So this is FBC, this is FBA, as you can see. Now I can plug in the values again here, and we can get the values. So theta equals tan inverse FBC and over FBA. So we can write this as tan inverse. FBA is 6.4 times 10 raised to the power negative 7 over 5.7 times 10 raised to the power negative 7. So on solving, we will get theta equals 42 degrees. So it would be approximately 42 degrees. Now we can write the final answer, which is 8.6 times 10 raised to the power negative 7. So for direction, we can see initially we can say the object was at west, but then it has been rotated by angle theta, and that angle theta is 42 degree. It has been rotated to south. So I can write initially at west 42 degree, then move towards. We got 8.6 times 10 raised to the power negative 7 west 42 degree south as our net force. So F net with the magnitude and with the direction. So in this lesson, we use Newton's universal law of gravitation to calculate gravitational force. We also saw that gravity is always attractive and that gravitational force between two objects form an action-reaction pair. Then we connected capital G, the universal gravitational constant, with lowercase g, which is acceleration due to gravity or gravitational field strength. Finally, we used vector addition to find the net gravitational force on sphere B when two gravitational forces acted at right angles. So the biggest reminders from today are: use center to center distance for R, and gravity always pull. Do not cancel action reaction forces because they act on different objects. And for the net force, always check the directions before deciding whether to add, subtract, or using the Pythagorean theorem.